Today in the lab we're going to do the pendulum experiment. And you might say, well, haven't we done the pendulum experiment? Yeah, you did that the first week in class, but this has got a couple different twists to it. So the first half of this experiment for pendulum is the pendulum period versus length. And that's what you did the first week, very crudely, very quickly, with only three lengths. So one of the big differences today is you're going to measure carefully 6 different lengths. And the lengths should be from 10 centimeters, about like so, to a meter, like so. So the length should definitely vary. Some of the people that did the lab, the first lab, didn't use a wide enough range of values, and they didn't get really good results as a result. So, of course, our formula is the formula you've been using and are familiar with. The period is 2 pi times the square root of the length divided by g. And the length is the length of a simple pendulum, which means, as we learned last time, as we wrote it as L plus R, where R is the radius of the pendulum bob. We're using the same pendulum bobs. They're 1 inch diameter bobs, and so the radius is 1/2 inch. Convert that to centimeters and add it to the length in centimeters, or you're welcome to measure it with the calipers. Make sure it's definitely a 1 inch diameter bar or rod. So 1 inch diameter sphere. Okay, so nothing new here, but we're not going to, the other thing that's new is we're not going to plot period versus square root of length. We're going to plot period versus length. And therefore, we're not going to get a straight line. We're going to get a curve that looks something like that. And so you're going to get 6 data points. And you're going to go to the curve fit menu, and you're going to find an equation that looks like this, such as y equals ax to the n, where n here is 1/2, and a is 2 pi over the square root of g, and n is 1/2, where x is really the length. Okay, that is the real length of a simple pendulum, L plus R. So this is what you're going to graph using. You'll find on the menu in the curve fit list, you'll find an equation that looks just like that. It may have a b there, which basically says, of course, b is 0 if the length is 0, b is 0, and the period is 0. So b should be 0. And you probably did that in your first lab also. So don't worry about b. If there's a formula that's got a b in it, fine, that's going to be 0 anyway. So we're looking at this formula, which fits a curve like so. It's obviously not a linear curve. So that's one difference. It's a major difference. The other major difference is we're going to then fit the data to the curve and compare the data, as we did from the first lab, to 2 pi over the square root of g and the exponent to 1/2. That's different because we already took the square root. But we're not going to assume that this is a purely square root relationship. We're going to see how close to this, to 0.500, this n is. That will be a source of error, or a source of difference between your real simple pendulum and the ideal simple pendulum. So that's part 1. And it uses the curve fit routine instead of a linear fit routine. Okay, part 2 is a little bit different. You remember I said, or you read in the lab, to swing the pendulum bob only just a little bit back and forth. By the way, when you start this experiment, the photo gate, which is accurate to 1/10 of a millisecond, and you might want to change your data table when you get the data and you go to get the error in the data table, you might also click on that box that also has uncertainty in it. There is a, above that, there is a decimal and significant numbers box, and please check the decimal box to make it 4. There was already 4 in the box there, significant number box, but just change it to 4 decimals because that's 0.0001 plus or minus 0.001, 1/10 of a millisecond. That's the error in the accuracy of the photo gate. So switch it to 4 decimal places, not 4 significant figures. And also click the uncertainty box to get the uncertainty in the result. Okay, so the second part is something we haven't done, and it has to do with the fact that, again, you don't swing this pendulum too far, because the formula that I had written down for the first lab, and it'll also appear for the first part of this lab, assumes you're swinging it only through a small distance like this, a small amplitude. The distance you swing it is called amplitude. So swing it through a small amplitude. When you do the experiment, both part 1 and part 2, just release the pendulum and let it swing back and forth a couple times, and then push the collect button. The computer will start the collection of data, and you don't have to start it and stop it just by pushing the button at the same time you start it and pushing the button at the same time you stop it. Just let it collect 10 data points, 10 periods for each of the 6 lengths, and you're going to plot that. The second experiment is the fact that the length of the, here we're going to keep the length the same, about a little less than 1 meter. And I'll show you the apparatus a little bit later. It's set up so that when your pendulum length stays constant and is like 0.99 or 0.98 meters, 98 or 99 centimeters, but the overall length of the pendulum, including the radius of the bob, is going to be about 1 meter. Okay, so we have a little curved scale to use, and it's set up based on the radius of about 1 meter. So this period then is going to be look something like this. That is, this is called the period for small oscillations. The 0 means pretty close to 0, that is small amplitude. So the 0 stands for small amplitude, and that's the formula, 2 pi times the square root of L over G. That's what T0 really is, formula we've been using today and also a couple of weeks ago. Plus there's this extra added term, which is T0 over 16 times A over L squared. And actually, there are more terms. There's a 4th order term, there's a 6th order term, and so forth. But this is going to be an approximation to what we call the first order. That is, this is the 0th order, and this is the 1st order correction term. A, of course, is the amplitude, and L is, of course, the length of the pendulum, which is going to be about 1, pretty close to 1 meter. And so this number is going to be about 1, and so this is going to be T0. It's going to be about 2 seconds. A 1 meter long pendulum has a period of about 2 seconds, divided by 16, times the amplitude as measured along an arc of the circle that it swings in centimeters squared. So this is a correction term. As you can see, gets bigger and bigger in a squared fashion as the amplitude increases, because L is a constant, this is constant, and so the only thing that's increasing here is the amplitude. So when you graph this, you're going to get a plot that looks like this, period versus time. You're going to get a graph that looks like this. This is T0. And this distance here is this correction term. I've exaggerated that distance. If you just graph this with T0 like this, which is about 2 seconds, it's going to look like pretty much a straight line. So what you've got to do is start your origin not at 0, but at, well, the best thing to do is hit your auto scale button. And that will auto scale your data. It will fill up the screen with your data, and the screen will look like this. Okay, this will be about 2.00 seconds. This will be about 2.01 seconds. A very small, roughly 1% correction factor. So your data will fit along this line, but they won't fit it as nicely as the first part because of things like error resistance and tricky measurement difficulties and so forth. So you'll get a little bit less accurate results than you do with the first part. And the first part should give you really, really close to the theoretical value. I'm expecting you should have less than 1% overall error in that experiment. The difference between 1/2 and what n is, and 2 pi over the square root of g, which you probably may remember is 2.007. The difference between your number and that's going to be less than 1% different, I think. So this is what we're looking for. Click on the blue A button, the autoscale button, to make it look not like that, but like this. Fill up your screen with your data, as always. Use the print graph option, and we've tried to set these all at printing like this instead of like this, landscape instead of portrait, so you get a really nice big graph with nice big numbers that even I can read almost without my glasses. Now the formula, there is no formula in the curve fit formula that looks like this. So you're going to have to make your own formula up. And there's a little option in the curve fit menu that says define function. So you want to define your function, which is going to look something like this. T equals T0. That's the formula that we used to have, 2 pi over the square root of L over G, plus B times x to the n. Okay, so this is 2 pi times the square root of L over G, which we call T0. And this is the second order, this is your first order correction term, where B is equal to T0 over 16 times the square root of times A over L squared. So that's what B is. N squared is what the power of n should be. This is a curve that moves upward like this, gets bigger and bigger correction as you move to bigger and bigger amplitudes. Fit your data and discuss how your data fit this formula and the theoretical value. That's it. This is an arc which has a radius of about 1 meter, so that the ball will just follow up just above the scale, just about where it is now at 0. You may see a little dot on the curved scale here that represents 0, the 0 amplitude, and that's where it's kind of wobbling around 0 amplitude. So I've got that set up so that it's basically at 0 amplitude. So we're going to do a quickie part 1. You're going to do more. You're going to do 6 measurements and 10 periods each. I'm just going to do 3 measurements and 5 periods each, but you get the idea. So go to Logger Pro, File, Open, Probes and Sensors, PhotoGate, and down at the bottom here is Pendulum Timer. Okay, hit the Connect button to activate the Collect. Turn that button green so that you're connected to the interface. And then we're going to, again, you want to take 10 periods and 6 lengths, but I'm going to take one period, 3 periods and just 3 lengths just to show you how this goes. So I measured the length carefully. There's 2 ways to measure the length. You can measure the string and add the radius to it. I measured from the top using the top of the meter stick, which I know you shouldn't do. It's actually I looked at this meter stick, it's 1 millimeter longer. It starts at -1 millimeter instead of 0. So I read 99.5 centimeters, and I'm going to add a 1/10 of a centimeter, a millimeter to that. So it's 99.6 centimeters. So 0.996 meters. Let's do this and pull it back a few centimeters and let it swing, and just hit the collect button whenever you want. I'm going to do it for 6 times. You're going to do it for 10 times. Okay, there are 6 readings. Statistics. And it says that I've taken 6 samples. You can see from the parentheses here I'm including 6 samples. You want 10 samples. And the median, we've got to change this to, double click on this, change it to 4 decimal places, because this is accurate to 0.0001 seconds, plus or minus. So we have 2.0026, 2.0027 is the mean, and that's at 99.6 centimeters, or 0.996 meters. Okay, let's do this at another length. Okay, stop it, and we have for 62.621 meters, we have a mean of 1.5462 seconds. All right, let's do one more. Okay, there are 6 periods, and so the average is 1.0528 seconds. So let's put those data in the list here. Go back to Logger Pro. And again, we're plotting period versus length, not square root of length, period versus length. You'll have more data points and probably better data points. But we need to go now to the Analyze menu and the curve fit. A times x to the b. The formula here is c times x to the n. Let's see what happens. So again, you'll have more data points. This looks like it's fitting the data very nicely. So b is the power to which the length is raised, which is plus or minus 0.025. So that definitely includes 0.500. And the value for a is 1.994. It's a little bit off from 2.007. The value is 0.199 plus or minus 0.03, but that includes the value 2.007. So this is the setup for part 2 of the pendulum experiment. We're going to do only 3 swings instead of 10 because air resistance is going to slow this thing down, and it's not going to be moving at the same amplitude, with the same amplitude after 5 swings, certainly 10 swings, and maybe even not quite 3 swings. So I'll move this back to 5 centimeters and start the program. You don't want to wait too long on starting the program here, because every time it swings back and forth, it's going to lose a little bit of amplitude. So you want to have the program ready to go, actually running. Since the ball's out of the way, you can just move it up to 5 centimeters, and then the program will start as soon as the ball goes through the gate at the first time. And release it, start the computer, and let it swing 3 times. And then as soon as it swings 3 times, just catch it. And the computer should have 3 periods for you to process. And we see that the period is, and don't forget to set your sensitivity to 4 significant figures. 4 decimal places instead of 4 significant figures. So we have 4 significant figures, and you see there's a variation only in the last digit. Again, this is a 1 meter pendulum, and it has a period of about almost exactly 2 seconds. So what we need to do now is simply get an average, and it's pretty easy to average this, but let's try this anyway. If we go to the stat option and the statistics option on the icon list, you will get, first of all, you have to stop it. Okay, so the statistics for this, again, we need to change this to 4 decimal places, so double click on that, change it to 4 decimal places, okay. 2.0023, that's the average, and the standard deviation is 0001, which is good. That's as accurate as this timing program works. So we have our first data point for a 5 centimeter amplitude of 2.0023. Then you want to proceed to 10, 15, 20, 25, all the way up to 50, which is the end of the scale, and then you'll have a data set. Then you have to enter your data set. All you need to record is the average, the mean period here to 4 decimal places, and the amplitude over there, and we're going to plot period versus amplitude, period vertically, amplitude on the horizontal scale. So we'll do, pull up 20, the period is 2.0077, and the standard deviation is 0. It's even better than 0.001. Now I'm not doing all the runs, I'm just going to do 3 to demonstrate what this looks like. So we'll go to 40 centimeters next. And you want to go up to 50, but let's try 40 centimeters. And hit the stop button, and the value is 2.0236, that's the medium value, and the standard deviation is 0.004. You might say, well, that's not very good. It was like 000 before, but the problem is air resistance is playing a big part in what's happening here, and so the period is actually, you can see it here, the period is actually significantly decreased from 2.0265 to 208 to 206. So the amplitude's decreasing, but we're going to be pretty close to 40 centimeters. That's why we only do 3 swings, because it keeps slowing down, and the amplitude is slowing down, or is reducing, and the period is getting smaller, slightly smaller. Okay, so we have these 3 data points. You're going to get 9 or 10 data points. Let's go put these in a table. So, okay, so here are data points. There's the 40, there's the 20, and there's the 5 centimeter data point. So pretty clearly this is a curve that's doing this. Let's go to the Analyze menu and to the Curve Fit option. And there's a graph there of our data. And there is no handy-dandy formula, so we're going to define our own formula. C plus B times, that's my function. So I only have 3 points. You're going to have 8 or 9 or 10 points. And it looks like the fit is very nice, and so I'm going to hit OK. It's going to give me the value of C and B and N. Okay, so C is 2.002. That should sound familiar because that's T0. That's the period of small oscillations, which is 2.00. Let's see, we can even change that to 4 decimal places again. Okay. We need to put the length, the amplitude in meters, standard MKS system, and the period in seconds, of course, standard MKS or SI unit. So when we do that, we get C is 2.0019, and that's actually T0 if you look at the formula, equation 3 in the handout. And you may remember that the period was actually 2.0023 seconds, which is really, really close to that. And B is actually T0 divided by 16 L squared, and L is about 1. almost exactly 1, so it's about 1/16 of T0, and that's about right. 1/6, that's actually 1/8 times 2, 1/8 times 2 in the denominator is 1/16. So B is just about exactly a 16th of C, which it should be, and N is 1.90 instead of 2, and that's because of air resistance at the upper level makes that N value smaller than 2, theoretically. So again, you'll have much more data, and that will actually give you a coefficient of correlation that's probably not as good as mine with only 3 data points, but it's a better result anyway. So that's part 2, and we've shown that indeed the first correction term is a power of 1.9 here instead of 2 for the reason we just talked about. And the value for B is pretty close to, check it out, T0, that's C, divided by 16 times L squared. Again, L is almost exactly 1, so it's about C divided by 16. And compare your B value to T0 over 16 L squared. So that shows you curve fitting of a different style that we can fit our curves to some theoretical relationship and see how close we come to that. And if we don't have a theoretical relationship, we can develop it from here. Looks like N is pretty close to 2, so theoretically this should be exactly 2.